Okay, good morning, class. Can you hear me? Okay, thanks for the response. So we'll continue our class today, with the second topics, that is solving the linear system. So before this, I think we are having the access problem in e-learning. Yeah. So for this homework already due, and you want to submit, you cannot submit due to the system problem. You can submit when the system recovered. Yeah. Okay. Now, we have discussed about the elimination method, yeah, and we look at the examples on how to solve the Gauss eliminations and Gauss elimination with partial pivoting. So later on, we will look at the example, okay, on how to solve it, okay. And then today also we will cover the methods, LU methods, yeah, LU methods, which is Doolittle and also Korosky, yeah. So we will look at these three methods. So for the system of linear equations, yeah, we can solve it using the Gauss eliminations. So have we discussed about this? I think haven't, right? The exercise. Okay, not yet, huh? So I show you the template of the table. Okay. So solving a Gauss eliminations method with partial pivoting or without the partial pivoting, we actually can form the table like this. Yeah, you can form a table like this. You put a matrix here and you put the operations. So after these operations, you obtain this matrix, and after this operation, you obtain this matrix. Yeah, so we will try to do it. Yeah, or you want to use the way like this. Yeah, from the matrix, and then you put the arrow, and then you write down what is the operations done. Yeah, and then what is the new matrix that you obtain after the operations. Also can, no problem. Yeah, so it's up to you which format you prefer. Yeah, but here I will show you how to solve the Gauss eliminations and Gauss elimination with partial pivoting in the table. Yeah, just use the table to present our answer. Yeah. Okay, so for these questions, okay, we have two of it, Gauss eliminations, Gauss elimination with partial pivoting. So draw the table. Okay, so split it into two column. Then we have the matrix. Put in the matrix and we have the operations. Okay, what's the matrix? You put it into the augmented matrix form. Okay, this is matrix 3 times 3. We use the vertical line to split the B and also the matrix A. Okay, so based on what we have discussed before this, yeah, if you want to solve it, okay, we will normally start from the calculations of MI, M21, M31. Okay, try to recall. Yeah, this is the first steps. So we put it here. We're going to calculate what is a M21. Yeah, M21. Okay, this is just a Gauss emissions. Okay, try the first one. So without looking at which one is the largest absolute values, we just continue with the steps, yeah, to find what is M21. So this is, okay, 21, A21 is 3.1, okay, divided by 1.4. Yeah, then we perform the operations, minus M21, R1 plus R2, we get the new R2. And then we have M31. So A21 is 5.6, then we have 1.4, okay, calculate, okay, equal to 4, M31 R3 equals to new R3. So based on these operations, now we are going to update our matrix. So the first row normally remain the same. So write down first row and second row based on these computations. Okay, M21, you put it here, minus 2.2143 multiply with R1, which is 1.4, plus R2, you should be able to get 0 or approximately equals 0. Then for the rest, same. Okay, so you can set this operation in your calculator to find the new R values. So in your calculator, maybe you can use A and B or X or Y, okay, up to you, okay, to replace R1 and R2. Yeah. So put in your calculator. So minus 2.2143 multiplied with R1 plus R2. So you get the next values. Okay, next, same. There will be many decimals, yeah, here. Okay, 87, 0.2143. Okay, so small matrix. So I should put a larger one. Okay, next, okay, we have this M31 equals to 4. So put in minus 4 here and then multiply with R1 and then plus R3. You should be able to get 0 or approximately equal to 0. Then same, okay, for the whole row, you perform the same operations. Yeah. So this is a new matrix. And now we go for the M32. If M32, then this is A32 divided by A22. So we have 17.4. Why we divide it with this? Because this is a pivot element, yeah, the diagonal. We want to reduce this to be 0. Yeah. So we set this. So normally for numerical methods at these chapters, we okay, this one. Okay, we don't have the so-called different types of steps. Like you want to, first of all, you divide the first row with the 1.4 and make it 1, or you do the rearrangement first. No, we just follow these operations. This is fixed. This is the number of the matrix is changing. Yeah. So we have 1.1895. Okay, this is M32 now. Now we are going to update the R3 based on R2. Okay, find the new R3. Okay, now first row and second row is the same. Okay, now 0. This one, after this operation, you should be able to get 0. And I put in R2 minus 23 point something here. R3, you put it here. You get the new values. Okay, same for this. Yeah, run the operations here. Okay, so after these steps, now you already have the upper triangular matrix. Then you just solve it by using the backward substitutions. And calculate what is the x3. Yeah, solve this problem. If you want to have the details steps, you can do that, or you want to use a calculator, also no problem. So I want to show the detailed steps, maybe you can do it here. Okay, find what is x3. minus minus or plus 1.7470, and then you continue again with the x3. Now you put in into the second equations and you solve for the x2. Again, try to check the answer. And with the x2, x3, you put it here, x2, x3, and solve for the x1. Yeah, so that is the approximations for the system of linear equations. Yeah, so just one table, show the operations. Or maybe some of you prefer to do that, also no problem. Okay, you prefer to use this matrix and use arrow. Then you say you perform the operations M21 R1 plus R2 minus M31 R1 plus R3, and then you get another matrix. Then get another matrix, no problem. Yeah, or you want to put it into the table. Okay, so this is Gauss emissions. Yeah, solving the given system of linear equations.
The
Yes,
the x2 and x1 how to obtain?
x2 and x1. Oh, you
Yeah.
want me to show you the detailed steps, huh? Okay. Okay, now I'll show you detailed steps. Okay, so for the second equation, now we convert into the equation 2. So these equations, if you write it, 14.6286 x2 plus, okay, this minus 23.0787 x3 equals to minus 0.2143. Yeah, yeah. So for it, now substitute this x3 into here. Yeah. Okay, 1.7470 equals to, yeah, so solve for the x2. So this plus this multiply this divided by 14.6286. This is 2, sorry. Yeah. And after you get this x2 equals to, where's the answer? Okay, 2.7415. Okay, done. Then you go for 1.4 x1 minus 3.4 x2 plus 8.3 x3 equals to 2.4. Yeah, so do the substitutions here, backward substitutions here. X2 just now 2.7415. Okay, solve for the x1. Yeah. Okay, is it clear? So that's why I say you can use calculator. Use calculator means what? Means you can just put in these all coefficients in your calculator and you can just skip these all steps. For me, that is okay. For other section, I'm not sure. Yeah, for me, if you want to skip these all manual steps because you say want to save the time, because that is just about solving. Then you can just give the answer directly. Okay, so x1. Okay, give here. Okay, you can skip these all detailed steps. Just write down x1. Okay, by backward substitutions, you got the answer. What is x1? What is x2? What is x3? That is acceptable for me. So maybe you can put a remark. Okay, use calculator to solve it. Yeah, for this step only. Okay, so you want to see whether your answer is correct or not after these long steps. You can also use a calculator to solve for the actual solutions. And then you compare it with the one that you solve it using Gauss equations. Okay, is it clear? Okay, now we go for the next questions. Okay, next question, Gauss emission with partial pivoting. Now we try to see same format. Yeah, we draw the matrix. Okay. How many steps? We're not sure. Okay, just put it here. So we go for B, matrix, and this is operations. Okay, put in the augmented matrix in. So same matrix, but just we want to see if we consider the partial power thing. So what should we do? Okay, operations. Now, before we continue to find the M21 and M32, this is under Gauss elimination with partial pivoting, so we have to check on the absolute values. Yeah, sorry, the pivot element. The pivot element normally, okay, when we start to do the Gauss Jordan eliminations, you look at these first values. Right. So you want to see compared to the in the same column, compared to the two values below it. If this one the largest absolute value, if this is not, then we have to do the row interchange. For this question, actually, you can see row 3 first values actually is larger than the first values in the first row. So it shouldn't be a smaller values located here. So we do the row interchange. Okay, we swap the row 1 and row 3. Now we go for this new matrix. Okay, after these operations, we have 5.6. Now remember the whole row, yeah? Interchange the whole row, not only the number. Okay, so check again. This is the largest compared to the two values below it. Then we can perform the operations. Okay, find the M21, same process, yeah, M21. So we have the 3.1 divided by 5.6. Okay, so the operations minus M21, R1 plus R2, we get a new R2. And also, we find what is M31. Okay, so minus M31, R1 plus R3. Okay, so we update the matrix. Okay, so the first row still the same. Now we want to find what is a new row based on these operations. Yeah, set this in your calculator. 0.5536, you put it here. Then this is R1, this is R2, R1, R2, R1, R2. Then you just key in the values in, then you can get the answer. This should be, if you didn't get 0, yeah, for these two, means that something wrong with the operation, you have to check. Yeah. Okay, so continue. Okay, done. And in the next steps, you know that you are going to reduce this minus 4.35 to be 0, right? So before doing it, you have to double check on whether this primary element is larger than the value below it. For this case, yes. If let's say, yeah, these values, this A22 is smaller than A32, then you have to do the row interchange. So for these questions, again, we will just continue to find the N32. Okay, we take this one, minus 4.35. So in this case, you can see the M21, M31, M2, M32, it should be less than 1. Yeah. So we're going to update the R3 based on the R1 and R2, sorry. Yeah. So because R2 here, the pivot element is at the R2, A22. Okay, then we will see what happened to the next. Okay, so row 1 and row 2 still remain the same. They should be you should get 0 or approximately get equal to 0. Sometimes you may get something like this, 0.0001. Just round it to 0, yeah, because of the rounding errors. Round it to be 0. Okay, next, update the values here using these operations. Put in R2, put in R3, so we get a new R3. Okay, and this one also. Okay, now back to this form. Yeah, we can use a backward substitutions. Okay, so we start from the third equations. X1, sorry, this is X3 equals to 5.8153. So solve for the X3, you will get yeah. And next, solve for the X2. Yeah, put in the X3 here, find the X2. Then find the X1. Okay, so you can compare the solutions with this. This should be similar. Yeah, they should be similar. Okay, 1.7464. This one 1.7470. And then X2 2.7415. This one is 2.7407. And the X1, yeah, X1 is negative 1.9 something. This one is negative 1.985. Yeah, so it should be a little bit different because one is without the partial weighting, another one is with the partial weighting. But anyway, you can see which one will give you the smaller errors. You can calculate these actual solutions using your calculator. And then you can use either one norm or two norm or maybe the infinity norm to measure, okay, which one will give you the answer that is near to the actual solutions. Okay. Okay, any questions for these Gauss equations with partial weighting? Okay, yeah. So basically, if we have a question like this, yeah, this is another question, a soft solution you can find in the textbook. For those who buy the textbook, later you can check on it. Yeah. So same thing also. Yeah. For this question, we do the row interchange for twice. Why? Because for the first one, we check on the row. this should be the pivot row. This location, it should be for the pivot element. Yeah. And then for pivot element, you have to check, okay, whether it's the absolute largest values. If that's not, then we have to do the row interchange. If let's say this is minus 4, so we only look at the absolute values. That means we still need to do the row interchange. Yeah. Okay, after the row interchange, you perform this, and then you get these values. And now you know you're going to reduce this to be 0. And then before that, okay, you try to check on whether this one is the largest or this one is the largest. Absolute values. Although this is a negative values, but these negative values, absolute values, okay, divided by 2 is actually larger than 7 over 4. Therefore, we will do the row interchange. Yeah, R2 with the R3. So after you do the row interchange, not only for these two values, but the whole row 2 and row 3. Then only we proceed to find what is the M31, M2, M32. Yeah, this is M32. And perform the operations and solve it using the backward substitutions. So for this column, okay, after you're familiar with it and you know how to key in these all values in your calculator and get the answer that way, then you can do that. Yeah. Okay, so that is the Gauss eliminations with and without partial pivoting. But for our assessment, most of the time you can see on the partial questions, you will have the questions for partial pivoting. Because Gauss eliminations method without the partial pivoting, actually you learned it before, I think in EM1 or EM2. Yeah, so for this part, okay, we introduce partial pivoting. Yeah, so that is a scope for your assessment. Okay, now if no questions for these Gauss eliminations, so after this hands-on exercise, I will go to the next method. Yeah, the next method is LU decompositions. I'm not sure whether the e-learning can be accessed or not. You cannot access, then you can just look at the slide. Yeah? Okay. Now, solving the system linear equations. Okay, we have the LU method. So what is LU decompositions method? I have a slide here. That is another set of or another methods, yeah, for us to solve the simultaneous equations. But you may ask which one is better, Gauss eliminations or LU decompositions, or maybe iterative method. This really depends. Yeah, depends on the data that you have. Depends on the types of system linear equations. So until this chapter, you can see actually different types of matrix. Yeah, we will introduce different methods, different numerical methods. For example, Thomas algorithm. Normally we use it to solve the tri-diagonal matrix. For the Korosky method, normally we just use it to solve the symmetric positive defined matrix A. Yeah. And then for Gauss eliminations and Doolittle, actually it can be applied for any system linear equations. But see which one you prefer. So we have different types of methods here. Yeah? And then for this, again, I want to remind you, for those who have a textbook, yeah, under LU, yeah, LU method, LU decompositions method, yeah, we have Doolittle, Kraut, Thomas, and Korosky in the textbook, but Kraut is not included, okay, because it's very similar to Doolittle. If you understand how this Doolittle work, and then it will be similar for the Kraut as well. It doesn't mean that this method is no good, but it depends on the nature of the matrix A. Today I will just focus on Doolittle and also Korosky. Thomas, I will leave it to week 4. Yeah. Okay, now you look at Doolittle. Okay, Doolittle is under LU decompositions. LU. So what is LU? LU is actually come from the matrix A. We decompose this matrix A into the form of L multiply U, where L is the lower triangular matrix. Here there is explanations. Okay, lower triangular matrix, and U is the upper triangular matrix. Yeah, we use the L lower triangular matrix, U upper triangular matrix. So once we use the LU factorizations to separate the matrix A into the form of, or to rewrite the matrix A into the form of L and U, then we can just solve it using in more efficient way. Yeah, you can find the answer in more efficient way. Okay, so this is a general example. Okay, for LU matrix. If that is matrix 4 times 4, so this is how the lower triangular matrix look like. If that is upper triangular matrix, this is how the matrix look like. Okay, upper and lower. This is lower, this is upper. Yeah? And now, do little decomposition. This is in general form. Maybe I'll show you the one with the matrix 3 times 3 first. Yeah? Do little, yeah? Do little factorizations. Look at this example. And LU decompositions or LU factorizations, actually, you know, okay, for matrix A, you write it into the form of LU, and then after you have the LU, then the next step is we will let the Ly equals to B. Solve for the Y. After you got a Y, you let the Ux equal to Y and solve for the X. Yeah, so let's see the specific example, how to solve it. Now, in these two little factorizations, all the diagonal of the lower triangular matrix, it must be 1. So that is two little factorizations. Yeah, so meaning that lower triangular matrix 1, 1, 1. If that is matrix 3 times 3, the diagonal A11, A22, A33, it must be all 1. A, B, C. Yeah, so you look at here. Solve this system of linear equations in the example 2.3. First of all, we extract the matrix A. So this is the matrix A. Matrix A consists of all the coefficients in the equations. Yeah. So 3, 2, 5, and so on. So this is matrix A. Now you want to write this matrix A into the form of L multiply U, where the L here, all the diagonal, it must be 1. Okay. And for the U, now U is just a normal upper triangular matrix. Yeah. So for those little factorizations, normally if we don't know what is L and U, we just put the unknown into the two matrices. So A, B, C, this one you put it as P, Q, R, S, T, U. Or you don't want to have P, Q, R, S, T, then it's okay. You can write down E, F, G, H, I, and so on. Yeah, you can use any alphabets or any symbol to represent the unknown in the L and U in the initial state. Yeah, like what we have here. Yeah, if you want to like make it more specific, then actually you can see this is the lower triangular matrix. Yeah, and for two little decompositions, this is all 1, and below it you have the numbers, but you still haven't solved for this number, so you can label them as the L21, L31, and so on. But for me, I think using just one alphabet, that is fine. Yeah, because you have to write a lot. Unless you can just label it in the computer coding, then it will be easier for you to understand. Okay, where is this L21, L32, and so on. But for manual calculations, yeah, I believe that this will be faster. Yeah, you can use A, B, C, D, E, F, G, H, or you want to separate them. This one you use A, B, C, this one you use P, Q, R, S, T, U, also can, no problem. Now, remember how to do the matrix multiplications. L multiply U. So in general, okay, you do the multiplications and then you get this general form. And then we are going to solve for the 9 unknowns in these two matrices. How to solve them? You can do the direct comparison. Want to rewrite it also can, no problem. When you just want to refer, then it's okay. So P equals to 3. So we know P equals to 3. Direct comparison. Q equal to 2. So you have the Q equal to 2. R equals to 9. So R equals to 9. So you have already solved for the P, Q, and R. So next, how to solve for A? You know the P, but you don't know the A. So from this comparison, direct comparison, you know the AP equals to 2. So you solve for the A. A is, P is 3 just now. Okay, so you have the 2 over P as the A. And then once you have it, so next to the move to the next values, A multiply Q plus S equals to -1. Then you're able to solve for the S. Because you know what is the values for A, you put it here. What is a Q, you put it here. Then you solve for the S. So you can see the solution here. Yeah? You solve it one by one. Yeah? PQR, then B, A, S, T, C, and U. Okay, so as here we got these values. You can use the decimals or you can use the fractions. Okay, that is fine. So you can proceed AR plus T equals to 6. You know the A here and you know the R. Okay, R is 9, A is 2 over 3, so we solve for the T. Okay, T here according to the solutions that is minus 0.0000003. Yeah, solve it one by one. And then the last one, you can see. We proceed. BR plus CT plus U equals to -4. So the last unknown, actually B you know already, R you know, C you know, T you know already, U is the last unknown. Yeah, so put in the values in and solve for the U. Okay, and now after you have this all unknown, yeah, this all unknown, at the beginning you set it as unknown because you're still not sure what is it. Yeah, so after you get all the unknowns, then you can put it into the form of with the L. Okay, this is A, B, C, then P, Q, R, S, T, U. Okay, so start with the lower triangular matrix. We let the L, Y equals to B. What's L? Yeah, we obtain from here. Okay, Y, okay, put it as Y. Where you get the B? This B is come from the right-hand side values of the system. 28, 14, oh, in these questions, and minus 13. Okay, put it here and solve it. So we can use the forward substitution to solve it. Same concept like just now. Gauss emissions, okay, in the last iterations, we just solve it using the backward substitutions. But here, because of the lower triangular matrix, that it will form the seesaw linear equation like this. That means that you are able to find what is the y1 directly from this system. And after you get the y1, yeah, then you're able to find the y2. Okay, substitute the y1 as 28 here. This is y1. Solve for y2. And then after that, it's solve for y3 based on the y1 and y2. Okay. After the y1, y2, and y3, then we proceed to the u. Okay. So ux equals to y. Okay. So this is the values that you obtain just now one by one. Okay. And then this is the u. Okay. And x is the one that you want to find. Yeah. And y you just obtain from here. Previous iterations. y1, y2, and y3. y1, y2, and y3. And because of this is the upper triangular matrix, so you solve it using the backward substitutions. Okay, so solving it, you get the solutions. So after the long step, if you want to check the answer whether it's correct or not, you can just use the calculator, change the mode to equations, and put these all values in, see whether you get the same answer or approximately the same. Yeah. Any questions for do later? Do a lot now here. Okay, no questions, then we move to the hands-on exercise. Okay, look at one past year questions. This one of the past year questions. Question 1. Yeah. So consider the linear system below, sorry. Use Doolittle, okay, to solve the system. Okay, so everyone have the question with you? If you can't access e-learning to download the questions, maybe you can just capture the question from here. Okay, I just noticed that somebody asking the meeting password. You access this WebEx without password, right? So what's this? Zahira. Okay, every time when you message me, you text me, you PM me, please mention who are you, yeah? Who are you and from which sections? Your name and your sections. If not, I will confuse, okay, which you will come from. You come here, you text me and you directly ask me questions. I don't know who are you. Yeah. Okay, so Zahira, are you here? I think we don't need the password, okay? Just the link to access. Okay, never mind. Just proceed, yeah. Okay, do later. Okay, look at it. We know that we're going to extract the matrix A, and then you are going to write it into the form of LU. Yeah? So now look at the solutions. Oops, yeah, I have the solution here. I forgot to erase. Maybe I show you step by step is better. Okay. So matrix A, we extract the matrix A, let it equal to LU. So what is the matrix A here? Okay, this matrix A, 3, 5, 4, -6, 2, 2, 2, 1, 7. Put it as matrix A. Okay. Equals to L. Now L is the lower triangular matrix. For Doolittle, you have to let the diagonal of the matrix L to be 1. Yeah? And then here it will be 0. And we still don't know what is A, what is B, what is C based on this matrix. Yeah, just put it as unknown. So multiply with the U. U is the upper triangular matrix, so you should have the numbers here. So let's say I just continue with D, E, F, or you want to use P, Q, R, S, T, also no problem. Then make sure that these three numbers, they are 0. For matrix 3 times 3. Okay, so in general, okay, you find out what is the matrix here. After a few exercises, actually, you can see that this matrix here is the same for all the questions. It depends on what you set for the unknown. Yeah? Okay, just matrix 3 times 3 matrix multiply with the 3 times 3 matrix. If you forget the matrix multiplications, okay, please check it, yeah, your previous notes. We are not going to repeat on how to do the multiplication of matrix in this class, yeah. Okay, this is a general form. If you feel that you are weak in doing the matrix multiplication, maybe you can memorize it. Yeah. Okay, now we do the direct comparison to solve for those unknown. Yeah. So D equals to 3, E equals to -6, F equals to 2. Yeah, direct comparison. So I will write the answer here. Then after that, you solve for this. AD equals to 5. So AD equals to 5. You know what is D? Okay. So A equals to 5 over 3. So you do the same for the rest. AE equals to G. So equals to 2. Yeah. So you know the A, that is 5 over 3. So make sure that these calculations, small calculation is correct because you are going to bring these all values for the next steps of calculations. E minus 6 plus G. So you solve for the G. Then move to the next. Equals to 1. Yeah, this 1 here at these partitions. Solve for the H. You know the A. You know the F. So you know the H as well. Okay. And next, BD. Yeah, BD equals to 4. And now, which one is unknown? B is unknown. Because D, we know here, that is 3. So B equals to 4 over 3. Okay, next, BE plus CG equals to 2. Okay, B we know. E, do we know E? Yes, minus 6. How about C? C, we don't know. Okay, C don't know. G, 12. Okay, solve for the C. And the last term, BF plus CH plus C. Plus I, sorry. Equals to 7. Yeah. So B, we know it. F, we know. C, just found it. H is minus 7 over 3 plus I equal to 7. So solve for the I. Okay. So after you get all the 9 unknowns, now you have the L and U. So I will normally just proceed to Ly equals to B. Yeah. So what is the L now? Yeah. Put in the matrix here. Y1, Y2, Y3. Now B is the right hand side values. Want to check what is the right hand side values given in the questions? This one is a B. This is a B. And L, this now, this is L. And you have the A, B, C found here. A, B, and C. Just put it into the matrix. 5 over 3, B is 4 over 3, C is 5 over 6. Okay, so solve for the Y. Yeah, solve for the Y. For this part, okay, although you know that is about forward substitutions, yeah, but for me, okay, if if you prefer to use calculator to solve it, that is okay for me. Yeah, that's okay for me. For my sections, yeah, for my sections. Okay, solve for it. What is the Y? So very obvious, Y1 equal to this, yeah. Then you can do some manual calculation if you want. Okay, find the Y2, find the Y3. Okay, until this step, can you follow how to find the Y? Okay, so we proceed. The next step is ux equal to y. Okay, so actually I have the solution here. Yeah. So you look at what is the ux. U, this one. You found the D, E, F, G, H, I. Yeah, D, E, F, G, H, I. Put these all values into the matrix U. And x is actually the values that you want to find. Okay, you want to solve. If you're able to solve this ux equal to y, then that is the solutions. So what is a y? Y you just calculate just now. You bring it here. Yeah. And now solve for the x using the backward substitutions. You want to show it 1 by 1, over 18, x3 equals to 9.4176, x3 equals to, and then next 12, x2 minus 7 over 3, x3 equals to, also can, no problem, okay? It's up to you, okay? You have time, you want to show it in details, you can show it, but here we are not really testing you how to solve the system using the backward or forward, but you want to see, do you know how to use the do later method? So it will be the overall method, no, the overall of the methods do later. Yeah. So now we solve for the x1, x2, and x3. You get this set of values. If you are not sure whether it's correct or not, you can substitute this answer back to the system. This system. Yeah. You put in x here, 2.5, x2, 3.54, and x3 1.5 and see whether it's approximately equals to minus 10.74. Yeah. Or you want to do a quick checking. Yeah. I don't want to compare one by one. I don't want to substitute one by one. Just solve this system using calculator and compare the answer from the calculator with this answer evaluated by the do later method. Yeah. So this is the way you check the answer. Okay, guys, okay. Okay, any questions until here? If no questions, we have a 5 minutes break, yeah? So after the break, we will go for another LU method. Similar, yeah, similar, but we will see what is the difference. It's just like the Gauss emission with partial pivoting. So they will be a little bit different. So we will continue with the Koretsky. Yeah? So I will share the QR code again for those who come in late. Can scan it. And we'll have the break, 5 minutes. After 5 minutes, we look at the Koretsky method. Okay, class, we come back. Yeah. So now we look at this page. This page is about Clark factorizations. As I mentioned just now, Clark method is not included in our syllabus, but you can have a look on it. Yeah. Sorry. Okay. This Clark method is similar to the Doolittle, but the only difference is that the diagonal of the L is not 1, but the diagonal of the U, that is 1. So for the rest of it, yeah, how we solve it, still the same. Yeah. Okay, so we will skip this one. And now we go for the Korosky factorizations. Korosky factorizations or this method, normally we use it to solve the system of linear equations with the matrix A that is symmetry positive defined matrix. So you may ask, what is positive defined, or what is symmetry positive defined matrix? So look at the definition here. Before we determine whether you want to use the Korosky method or not, we have to check on the matrix A, where this matrix A is extract from the equations, yeah, the coefficients of each of the equations on the left-hand side. So to test it, again, we have these definitions, where if matrix A is a positive defined matrix, then X, vector X, transpose of the matrix X, multiply with the AX, it should be greater than 0. Okay, and vector of X, it is not equal to 0. So you want to test whether this given matrix A is positive defined. Yeah, and first of all, we check whether there is symmetry or not. Yes, okay, there is symmetry. If you forget what is symmetry, try to check symmetry matrix. How the symmetry matrix look like. And you proceed, yeah, based on that definitions. Here the xt, yeah, this x, x1, x2, x3, multiply with the matrix A, multiply with the x again, without the transpose, and you have to prove it, yeah. This will be always equal to 0. So how to prove that it's always equal to 0? So you can see in these steps. You have the x1 square, x1 minus x2 square, x2 minus x3 square, 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 and also this one also square. So it means that these values, it should be always greater than equal to 0. So this is by definitions. Anyway, we know that this is quite difficult. It's about proving something is quite difficult to show the step like this. Normally people will stuck somewhere here. And how do we write it into this form? Yeah, it's quite difficult. So since that it's difficult to show that the matrix is positively defined by definitions, therefore we can choose to use another alternative to prove that this matrix is a positive defined matrix. So normally I will encourage you to use a theorem 2.1 to prove that this matrix is a positive defined matrix. So first of all, you look at the matrix. If that is a symmetric matrix, then you can proceed to do the testing based on the theorem 2.1. Or if that is not symmetry, yeah, it can be the positive defined, but because of we want to use a Korosky, so we have to make sure that there is a symmetry positive defined matrix. So check the symmetrical, whether there is symmetric, then only we check for these conditions. Now, for this condition, although you have to check for 4 conditions compared to this, but this is quite straightforward. A, B, C, and D. These 4 conditions must be satisfied. Then only we can say this matrix A is a positive defined matrix. So we go through one by one. If A is a positive defined, first of all, we have to make sure that A is non-singular. How to check whether A is non-singular? We calculate the determinant. If the determinant is not equal to 0, then we say yes. Okay, this is an non-singular matrix. Then we check for the diagonal. Are all the diagonal, they are all positive values. This is the diagonal. A11, A22, A33. They must be all greater than 0. They mean positive values. If yes, then you move to the next step. This one is about the non-diagonal. It must be smaller than the maximum of the non-diagonal must be smaller than the maximum of the diagonal. So you can see absolute values here. If for these questions, non-diagonal, Okay, this is diagonal. For the rest of it, they are non-diagonal. So absolute values, it should be the maximum 1. 1 should be smaller than the maximum of the diagonal. That is 2. Yeah, satisfied. Then next one, D. Aij square, it should be smaller than Aii multiply Ajj. Example, you have to check for, if that is matrix 3 times 3, you have to check for A11 square. Sorry, this is Aij, yeah? Aij, so A12 square, whether that is smaller than A11 multiply A22. And also you have to check for A13 square, whether that is smaller than A11 multiply A33. And what else? You have the A23 square, see whether that is smaller than A22 multiply A33. And also have to check for the A21 square, okay, whether that is smaller than A22 multiply A11 and so on. These are all the non-diagonal, yeah, in matrix 3 times 3. But anyway, if you already prove that this matrix, you can just ask for this one, either this one when they are symmetric, A13 equals to A31, A23 equals to A32. Yeah, either one. Okay? If you make sure that this matrix is already a symmetric matrix, then you just check for one set. Okay? Okay, now before we go into it, maybe we look at one example. Yeah, we check on this one whether that is a positive defined matrix. Okay, so the quick one here. This is also one of the puzzle questions. Yeah? Okay, so first of all, of course, you won't use the definitions, right? If you want to try to use definition to prove it, that is fine. Yeah, that is okay. Or else, okay, we just use the theorem 2.1. Okay, find the determinant of the matrix. Remember what is the formula? If you can't remember what is the formula to find the determinant, you can use a calculator. For me, that is okay. Yeah, just key in this matrix in your calculator, and then go to options, find the determinant, and find out what is the matrix A. What is the determinant of matrix A? Make sure that that is not equal to 0. If not equal to 0, then you will say that is a non-singular matrix. So the first one satisfied. So try to find out later, okay, what is this determinant using your calculator. Second one, yeah, all the diagonal must be greater than 0. So very obvious, if you look at here, A11 equals to 1, A22 equals to 20, and A33 equals to 60. Oh, before this, okay, do we need to prove that is symmetry? No. Okay, no need to prove that is symmetry. Yeah. But then if you look at it, that is symmetry. 2, 2, 4, 4, 32, 32. Okay, that is a symmetry positive defined matrix. Okay, so I, okay, they are all greater than 0. Yeah. Therefore, the second condition also satisfied. Then now we go for the next. Okay, maximum of the non-diagonal. What is the maximum of the non-diagonal? So maximums of the non-diagonal Aij modulus equals to, okay, what is the maximum non-diagonal? Class, can you give a response in the chat box? For non-diagonal values, what is the maximum value? Anyone? No one? Yeah, okay, 32. Okay, to make sure that you are listening. Okay, so what is the maximum Aij. Sorry, Aii, sorry, Aii, diagonal. Maximum value at the diagonal, maximum value at the diagonal, 60. Okay, so is it satisfied the conditions? Yes. Yeah, satisfied conditions where we have this one. Actually, I need to put the modulus in front, yeah? Maximums of Aij smaller than maximums of Aii. Therefore, satisfied the conditions. Yeah. And the last one, because of this is symmetry, so we just test for A12 square. Yeah. See whether that is smaller than A11 multiply A22 or not. So A11, A12, okay, A12 is here, okay, 2 square, okay, and then you have the A11 multiply A22 equals to 20, yeah, okay, so smaller than, yeah, then we test for A13, A13 square, okay, 4 square, okay, go up a bit, see whether that is smaller than A11 multiply A33. So A11 is 1, A33 is 60. So this one is 60. So 16, yeah? Smaller than 60, okay. Okay, what is A23? 32, yeah? 32. 32 square. Okay, whether that is smaller than A22 multiply A33. So A22 multiply A33, 20 multiply 60. Okay, 1200. This one, what do you get? 1024. Yeah, still smaller than. So this condition also satisfied. So from these four situations, okay, if that is satisfied, then we can say yes, matrix A is a positive defined matrix. Yeah, so this is how we prove it. Okay, now look at the example. Okay, example. And before this, we will see how this method works. Okay, back to this Korosky factorizations. Yeah. So once you confirm, you have proved that this matrix A is a symmetry positive defined matrix, then we can proceed to the Korosky factorizations, where it is also the LU method. So it means that you will decompose this A into the form of L multiply U. And in Korosky, we will set it as L multiplied with the transpose of the L. So if L is a lower triangular matrix, if you transpose it, it will become the upper triangular matrix. So they are the same. So look at this example, 2.6. We extract the matrix A from the system. Then we want to solve for x1, x2, x3. There are 3 unknown in these 3 equations. Okay, we solve it simultaneously using the Korosky factorizations. So this is the right-hand side values, B. And now, A equals to L multiplied LT. So this matrix, it can be written in the form of L multiplied LT, where this is a lower triangular matrix. L is the lower triangular matrix. When you transpose, this matrix L, you transpose it, it will become the upper triangular matrix. So same like the Doolittle, we will do the multiplications. Normally they are the same for the matrix 3 times 3. Then after that we do the comparison. So this A, what is A? Find A. A squared equal to 4. So we will only take the positive values. We solve for it. So we set the A equals to 2. Then after that, with the A, you find what is the B. So AB equals to minus 1. So A equals to minus 1. So B equals to minus 0.5. So do it one by one. Yeah, same like the do little. So AD equal to 1. Yeah? So you know the A. So now you solve for the D. And in these decompositions, actually have only 6 unknown. Just now, do little. A, B, C. Okay, in the L. And in the U, you have P, Q, R, S, T. Another 6. But this one, because of L is a U is a transpose for the L. Yeah? So there are only 6 unknown here. Then you proceed, be careful when we calculate all these values. And after get all the A, B, C, D, E, F, then put it back to this L and LT. Yeah? So A, B, C, D, E, F. Yeah? Transpose it, become the LT. That is a U. And we will proceed to the same procedures. That is, we will solve for that Ly equals to P. Yeah? So we take what is the L just now? L. You want to skip this step, you can skip and go directly to these steps. You take the L, multiply with the Y, you get the B. Solve for the Y using the forward substitutions. If you want, you can show the detailed step like this. Or else, you can just write down what is a Y1, Y2, Y3. Yeah, this is about the forward substitutions. After you get the Y, then you continue to solve the Ux equals to Y. So for Korosky, this is LTX equals to Y. So what is the LT? Okay, put it here. X1, X2, X3 equals to Y. So you bring this Y to the next steps and solve it using the backward substitutions. These are the detailed steps. For me, that is not compulsory to show it in details. If you want to show, that's fine, you have time. But if you feel that, okay, I just want to solve it quickly based on this system, then you can just give what is the x1, x2, and x3. Yeah. So you can do the checking with the actual solutions. So your calculator, again, your calculator can give you directly what is the solution, so you can compare it with the solutions that you estimate using the numerical methods. Okay. So look at one more examples. Okay, before this, okay, any questions before we proceed to another example? A question you put in the chat box or you can on your mic. Okay, so far no, proceed, yeah. Okay, now, sorry, okay, come back. Okay, so this example, look at this example. Show that this matrix A, the matrix A, for the following system of linear equations, is a symmetry positively defined. Then, solve the system using the Korosky method. Now, this is also one of the past questions. Yeah. Okay, this system, we look at the matrix A, we extract it. And you found that actually this is not symmetry. If that is not symmetry, that is possible it to be the positively defined. But because of you want to show that is a symmetry matrix as well, so you try to think about whether that is possible for us to rearrange the rows accordingly and form a symmetry matrix. So for this case, yes. Yeah, you try to rearrange them and make it into the symmetry form, where you can see A12 equals to A21. A13 equals to A31. This is a typo, this typo in my notes. This A23 equals to 32. So that is symmetry. So after you rearrange the rows, yeah, or the equations, then it will give us the symmetry matrix. Yeah, and don't forget, if you do the rearrangement, don't forget this B as well. Okay, if you arrange the whole row, it should be arranged. So this row 1 go to the row 2, row 2 go to the row 3, and row 1 go to the row 3 go to the row 1. So we form this symmetry form, and then we will test for whether there is a positive defined matrix. So we check with the 4 conditions. First of all, you can check this matrix A, the determinant, whether that is not equal to 0. So you find out what is the determinant. 100 not equal to 0, show it. Second one, diagonal. All the diagonal, it must be positive values. So write down diagonal A11, A22, A33, they are all greater than 0. Done. Maximum of the diagonal. It should be larger than the maximum of the non-diagonal. So for this matrix, maximum non-diagonal is 14. Maximum diagonal is 45. So satisfied. Then because of this is a symmetry, so 1, 2, 2, 1, they are the same. So see whether they less than A11 multiply A22. So do the checking quickly. So we have the 6 square, 36, multiply with, compare with the 4 multiply 10, that is 40. Satisfied. Then next one is what? Okay, A13. 8 square, 64. Is it less than 4 multiply 45? That's it. And next, 14 square, is it less than 10 multiply 45? Yes. Okay, all satisfied. Then we can conclude that A is a symmetry, symmetry positive defined. Okay, then we proceed. We proceed to A equals to LU. And we know that for Korosky, this U, it should be the transpose of the matrix L. Write it into this form. And then now we solve for it. Step 1, it will solve for, now this one is writing step 2. So means that step 1 is to find out what is the L and U first. So Ly equals to B. So B, you get it from the system. 2, 4, and 11. Look at the letters B. Don't look at the one that without the arrangement. Okay, so we put it here. 2, 4, 11. Solve for the Y using the forward substitutions. And then this step you should be able to know, okay, how we solve this. And after that, solve for the Ux equals to Y. Bring the Y here. Solve for the x1, x2, x3 using the backward substitutions. So this is the answer. X1, x2, and x3. If you want to check, just put it back to here and see whether that is approximately equal to the right-hand side values, or just use the calculator to check for the actual solutions. Okay, so now instead of time, we will go for the hands-on exercise. Where's the exercise? Okay. We can refer back to the example given. Look at these questions. Okay, now we do it together. So this is a system of linear equations. So it can be written in the form of ax equal to b. Show that A is a symmetry positively defined. So I think this is the third questions. So but then we solve it together. Okay, so write down the A. Okay, first of all, we check for the symmetry. In this matrix symmetry? No, right? If you look at the diagonal, so it's not positively defined. Non-diagonal, 1 to 8, the largest. Diagonal, the largest 52. So how about we think about how to rearrange them? Okay, if you rearrange them, we will swap for which one? This one should be here. This one, we move it out. So we swap for row 2 and row 3. So what you get here? 4, 6, 8. Okay. Is this matrix symmetry? Yes, sir. Okay, so means that we swap this, yeah, swap these two. The whole equations, yeah, not only the right hand side, this one also. So means that B, new B, now is 0 minus 80 minus 226. Yeah? Okay, now we proceed to check for the first one. Okay, find the determinant. The determinant, if you put this matrix in the calculator, it gives you 4900, not equal to 0. Yeah, so the first one satisfied. Second one, okay, A11 equals to 4, A22 equals to 34, A33 equals to 129. Okay, therefore, we can say that AII is greater than 0. So satisfied. The third one, maximums of the non-diagonal, it should be less than the maximums of the diagonal. So maximum of the non-diagonal here is 52. 52 is smaller than 129. Yeah, satisfied. Okay, next. Since there is symmetry, then we will just test for 1, 2 square, 6 square, 26. So see whether that is less than A11 multiply A22. 4 multiply 34 equals to 136. Okay, so that's smaller than, no problem. 13 square. 13 is here. 8, yeah? 8 square, 64. A11 multiply A33. 4 multiply 129, of course. It's much more larger. Yeah. A23 square. 52 square. Yeah. So A22 multiply A33. Check on using a calculator. 4,000 something. Yeah. So this also satisfied. So this is how you prove it. Yeah. How you prove it for part A. Yeah. Part A. Prove whether there is a symmetry possibly by matrix. Yeah. Using this way. And now we'll go for the B. Okay, everyone okay with this positive define? Yeah, no problem. Yeah, no problem. There we go. To the A equals to L, LT. Yeah. So use the, oh, okay. Aij is diagonal values. Aij is the diagonal value when the I equal to J. Should I write something wrong here? This one actually I need to put in I not equal to J. Aij is the positions of the values or the coefficients in the matrix. So it depends. Yeah. So I have a question here. Aij is a diagonal. Aij is a diagonal. Okay. We cannot say Aij is a diagonal because Aij is just a labeling. Like A11, A A12, A13, A21, A22, A23, and so on. So, but here, you see, this is A11, this is A22, that's A33, sorry, A33, yeah? So, if the I equals to J, so that means they have the same values, so they are diagonal. Non-diagonal, yeah, where the I not equal to J. Yeah, so these are all the non-diagonal. That's just a labeling, yeah? Tinash, Devi, okay for you? Okay, yeah, proceed. Okay, just now we have the A. Use the one that you already make it into the symmetry form. Okay, matrix A equals to Korosky. So we have the lower triangular matrix with this form. Multiply. Okay, this is L, this is transpose. It's also the upper triangular matrix. A, B, D. Okay, this one also, you want to use PQRST also no problem. Or you want to use A11, A21, A22, also no problem. Yeah. So matrix multiplications, yeah. Okay, then we do the comparison. So A squared equal to 4. Therefore, A is 2. You take the positive values. AB equals to 6. So since you know what is a A, then B is equal to 3. So this is a quick one. Okay, you can solve it quickly. This is a simple calculations. So D here, A is equal to 2, so D equal to 4. Yeah. So continue, B square plus C square equal to 34. You know the B. Okay, so solve for the C. C here equals to 5. BB plus EC equals to 52. Yeah. So you know the B, you know the D, you know the C. Okay, now we solve for the E. Yeah, should be 8. And D square plus E square plus F square equals to 129. So 4 square plus 8 square plus F square equal to 129. Solve for the F. 7, yeah. So you get 49 here, okay, 5 here. You just solve for the F. Okay, then with this all 6 unknown, then we can proceed to Ly equals to B. So what is the matrix L? 2, 3, 4. Okay, A, B, C, D, E, F. Okay, Y1, Y2, Y3. Okay, B. Okay, go and find what is B. Here, use the new B, because that's how we do the row interchange. So we have to use this B in here. Yeah, solve for the Y using the forward substitutions. Okay, 0, negative 16, negative 14. Use calculator is faster, yeah. Okay, then you have the L minus 1 x, yeah, equals to Y. Okay, so what is the, not minus 1, sorry, transpose. Sorry, transpose, yeah? Y. Okay, transpose of the L just now. So you have 2, 3, 4, 0, 5, 8, 0, 0, 7. Okay, upper triangular matrix. Then solve for the x1, x2, x3 equals to the y. Bring the y here, 0, minus 16, minus 14. Okay, solve for this. And get the answer. Okay, so class, any questions until here? Okay, so try to find out what is x values. 4, 0, minus 2. Okay, so that is the steps. Huh? Yeah, no questions? Everyone can follow? I try to check the attendance here. I have 50 of you, but the attendance here is 55. Why? Some of you maybe you register and your name haven't appeared in the my M system. Yeah. So for each of the section, I think it should be around 50 only. So if have more than that, maybe sometimes the faculty will try to rearrange or try to balance the number of students in the class. Okay. Okay, waiting for questions. No. Okay, so next week. Okay, next week. Actually, our class is not affected by the holiday, right? Wednesday and Thursday. Just one quick questions. Do you want to have class next week?